Hello, everyone. Okay, let's keep talking about some other things, I guess. I have done much of this content in other places, at least one other place. I wasn't thrilled with the intensity of the chalk, so to speak, the clarity of the chalk and some of the clarity of the presentation, but mostly the chalk wasn't really that visible. So I'm trying to make this so that this is visible to anybody who's looking for obvious reasons. I mean, we learn this stuff by, looking at this, listening to this, and just trying to learn to the best of our ability. So hopefully this is going to be a little more clear as far as literally more clear looking at how sharp a contrast there is in the chalk and the board, and how clear the chalk is, and how strongly something's written. It's real good chalk, guys, so it should be pretty clear to us. Let me say a couple things here. In addition to that, when I had done this work earlier, I made I don't want to call it a trivial error. It was, any error is not that good. What I had done was, when I was doing the derivative of the cross product, I wrote the derivative of the cross product correctly as far as the final answer. What is the derivative of the cross product, A vector cross B vector? I found that out, and we were able to prove this, but when I was taking the derivative of the cross product, I failed to mention the derivative of the cross product. I just let the cross product be A vector cross B vector. You see that in the other work. There were enough other things in the work that I felt were worthwhile that I'm going to leave it up there as a film, but just be aware of that. So those of you in my classes, I'm putting this close to where I put the other film as well. There's things in the other film that should be of use to you, and let me get through this and we'll see to what level I'm going to take some other matters that I want to discuss as well. So it's good enough that I'm going to leave it up there, but be aware of the error that is present there, and I've also wrote that in the description of the film. That's something to watch out for. Well, what's going on here, guys? What do we want to look at? We are looking at the derivative of the dot product and the cross product and rotational dynamics. The derivative of the dot product, where the vectors under consideration are A vector and B vector. Well, what are A vector and B vector? Well, we've gone into that in other films in some relatively substantial detail, where I've talked about the dot product, where I've talked about the cross product, and that's at your disposal to look at whenever you choose to look at it, if you choose to look at it. Those of you in my classes that I'm teaching, I don't necessarily make that something required to be looked at, but it's always a good idea to look at stuff like that. So we've gone into the dot product and the cross product in very substantial detail elsewhere. We have talked about A vector and B vector, and we've labeled A vector and B vector very oftentimes, overwhelming majority of the times, we've labeled A vector and B vector as A vector equals A sub x I hat plus A sub y j hat plus A sub z k hat, and B vector is B sub x I hat plus B sub y j hat plus B sub z k hat. So A vector is AX I hat plus AY j hat plus AZ k hat. B vector is BX I hat plus BY j hat plus BZ k hat. AX, AY, AZ, BX, BY, BZ are scalars, but when you multiply them with the vectors, the appropriate vectors, whether it be I hat, J hat, or K hat, we're talking about vector quantities. And when you sum vectors, you get more vectors, or you get another vector. The sum of vectors is a vector answer. Okay, so we talked about that. So the scalar AX, for example, times the vector I hat gives you a vector. And then these are all vectors, sum the vectors, and you get the A vector. Same argument for getting the B vector based on these. Okay. Let's take the time derivative. It's frequently the one that gets used in physics. This is not something necessarily that has to take place for the mathematics to be valid, but it occurs so often in physics. Let's use the time vector. Okay. And in fact, we can, when we prove this to be true, we can take higher order derivatives as well, if we wanted to, for whatever reason. If for no other reason, just for the sake of the mathematics. I got the first derivative. Let me get the first derivative of the first derivative, which is the second derivative. Let me get the first derivative of the second derivative, which is the third derivative of the original quantity, etc., so on and so forth. Can we do it? Sure. Well, once we've nailed this mathematics down, we can do very many things. It becomes certainly more complicated, but once we know the basic argument of how the differentiation of a first order, involving a first order derivative, how the differentiation takes place, then subsequent differentiation is easy to do conceptually. It may be very tedious. Look, there's a lot of stuff here. I mean, once I've taken the time derivative, this thing's broken up into two items. Once I've taken the time derivative here, it's broken up into two items. Two terms up here, two terms up there. Now do another derivative. Now, do the second order, do the first order derivative do a first order derivative of the first order derivative. Well, this is going to break up into two terms, and that's going to break up into two terms. You're going to have four terms. Same thing here. Break up into two terms, break up into two terms again, and it's going to be four terms if in the whole process you're taking the second derivative. The third derivative, perhaps there's partial derivatives that get done. But all of that obeys what's going on here in some regard. This is the blueprint to any kind of differentiation. Partial derivatives, higher order derivatives, with partial derivatives being taken into account, or not being taken into account. But certainly with partial derivatives and any ordered differentiation that is allowed, for which the function is defined, for any ordered differentiation that you want to go, you can do it. Once you've got the first order differentiation under control. And that's what we're going to get to. And we're saying this is what the answer is. The derivative with respect to time of a vector dot b vector is dA vector dt dot b vector plus a vector dot db vector dt. Okay. The derivative with respect to time of a vector cross b vector is going to be dA vector dt cross b vector plus a vector cross db vector dt. They look alike in a sense. One's got a dot product there, one's got a cross product here. The order that you do the multiplication for a dot product doesn't matter. We've already talked about this in other films, very much. That's not an issue. We know that. Probably look at those before you look at this. Doesn't matter. At some point, look at them. I would advise looking at it, because the people whom I've quoted are excellent. Are great mathematicians for much of the math that we do. Same thing here. So here the order doesn't matter. Here it does. The order that I add them doesn't matter, but the order of the cross multiplication will matter. Okay? What is a vector cross b vector? Heck, this could be d vector cross f vector, and then just kind of put d's right here, put f's right here, and then go for it. Okay? When you do this, you get something of this nature. Okay? So that's, great. Now we remember this. Luckily, we have it on film, so you can always go back. I frequently forget that. I think I'm on occasion just lecturing something live and there's no way to go back, not getting filmed, but we can go back, so we're not worried about it. This is what we got to prove. Let's go for it. You know it. You can come right back and see that it's going to work, and let's see. And everybody's defined as they're defined, so let's not, we don't have to go back and forth too much on that. We'll look at it and see what we can say about it. Okay? So let's see what we can say. So we're looking at something like this. We're making a claim like that. By the way, I mean, while we're here, while we're at it, I guess you could speak. You could speak about it. We also know that if you're doing a vector dot b vector, and we've gone into this in just great detail, guys. A sub x b sub x plus a sub y b sub y plus a sub z b sub z.
So they're saying that too. Yeah, okay, that's we remember we derived that. Hey, that's a heck of a lot easier to remember than the cross product. That's for sure, right? But so we got this, and let's use that. Let's take the derivative of this quantity, which means we're taking the derivative of this quantity, and let's see if it really does give this okay as an argument for what's going on. We will do the same thing here. We'll take the derivative of this right here and see if it does all that. Well, tell you what, we got this right here. Let's erase a few things. Let's leave some things and erase some others, I guess you could say. See what we can say here. It's good not to erase any of it. I guess we had a lot of room and stuff. We could, maybe put this upward and it takes something down, I guess. Have some sliding boards or something like that, but we don't have it. So let's erase a number of things, and just remember, this is where we're shooting for, guys. This is where we're shooting for. Well, you got that. We have it. We can always go back, and we can always take a look. Like I said, like I said, we've gone into really big detail on the dot product and the cross product, and that went pretty decently, I think. Whereas when I did this particular one, I wish, regarding the derivatives of the dot product and the cross product respectively, that could have been a little more clear as far as even just the aesthetics of looking at the chalk, in addition to me being a little bit careless with the notation. I didn't leave the DDT on the A vector cross B vector. So not a problem. We're going to try to make sure that's not going to be a problem again here, guys. That's one reason I wanted to kind of get to look at this thing. But again, I also think like I said, the way the clarity of the chalk here really makes a difference, I think, and that's a big thing too. Even in the best of circumstances, if the chalk's not that great, then it's not the best of circumstances. Then it's just, even if everything goes smoothly, you want the chalk to be seen quite well when it's being done. All right, well, let's take a look here. We got A vector dot B vector, and we got A vector cross B vector. So A vector dot B vector, we have said that A vector dot B vector is AX BX plus AY BY plus AZ BZ. And it's the dot product of two vectors is a scalar function. dA vector ddt of A vector dot B vector is going to be ddt probably a number of ways to write this. I'm not sure what's the most convenient. Let me kind of write it like this. Right. Yeah. The differentiation of a sum is the sum of the derivatives. What does that mean? That means you differentiate each of these in and of them by themselves, rather. So you go d dt. The derivative of a sum is the sum of the derivatives. Yes, certainly. Now, the derivative of a product,
the derivative of a product is the sum of the derivatives. Forgive me, that's wrong. The derivative of a sum is the sum of the derivatives, true, and the derivative of a product is arrived at through the product rule. So let's kind of, it's not going to be the, the aesthetics aren't always going to be the greatest, but let's kind of like, let's go up here. Let's take a walk up here. Let's take all this and go up here. And what is this? What's going on here? We know this, we're working with this. This right here, let's go up here. The derivative of a product is given to us via the product rule, and that is dAx there's probably a number of ways we can do this. I'm already sort of arguing with myself how to go here. By the product rule, the derivative of the product ax bx with respect to time is dAx dt times bx plus ax dbx dt. That's the product rule for just one place here. So what we have here is just this. That's for this guy. Okay, so we got this guy right here associated with this. How about this guy? It's going to be the same argument. How about this guy? Same argument, you guys. It's the same format. You are doing the product rule across the board when you're doing something like this. So what are we getting here? We're getting day, forgive me, day dt by. Then you're getting ay dby dt. Plus, do it again. Same argument, guys. Throughout at this point, once we're doing the same thing. They all have the same format. And az dbz. So what we have here all right, well, what's going on here, guys? Well, I tell you what, I see some stuff here. I see definitely see a connection here. I mean, I think we look carefully enough. We definitely see a connection here. What's the connection? The connection is there's addition everywhere. So if there's addition everywhere, add everything the way you want to add it. Add it any way you want to add it. Just make sure you add everything. Tell you what I'm going to do. ax dbx dt, ay dby dt, az dbz dt. Add those three terms and kind of have them together. I think you know where I'm about to go here. dx dt, dax dt bx, day dt by, daz dt bz. There seems to be a pattern here too. Look at the top, look at the bottom. I truncated a couple things here as I'm making the big moves here, but you guys understand what I'm doing. We got this. We got this. Yeah. Well, wait a minute. This whole top thing is simply, you know, if you look at how the dot product behaves, you're putting x's together, you're putting y's together, you're putting z's together. Here are the x's, here are the y's, here are the z's, and there's a derivative right here. Yeah, there's a dAx, there's a dAx dt, a day dt, and a dAz dt. I'll give you the argument a little bit without maybe doing it on all points here. But if you were to say that dA vector dt is dAx dt I hat plus day dt j hat plus dAz dt k hat. Sure. Well, why not? Why go here too then? Well, wait a minute. Let's hold the phone for a second here. A vector is just ax I hat, ay j hat, az k hat. Well, wait a minute. If I take well, yeah, that's true. That's certainly true. Certainly true. And my preference was maybe not to have written that just yet. Let's stay with this guy right here for now. Definitely my preference to stay right here. Tell you what, I mean, yeah, that's what I just said here is right. There's nothing wrong with that. But why don't you match it up a little bit better? Or why don't I match it up a little bit better? Why don't we match it up a little bit better? Bx I hat, by j hat, bz k hat. Wait a minute. If you were to take dA vector dt, which is all this, and dot it with b vector, which is all that, the I hats go, and it's dAx dt bx, day dt by, so it's dAx dt bx, day dt by, dAz dt bz. Absolutely, that's what it is. It's the same argument right here, you guys. It's the same argument right here. This guy right here, if you were looking at, you know, it's again, it's debatable if you need me to do that, but that's, yeah, sure, that is what's going on. And so what is it? I mean, what's going on here? Well, what that is basically what we just said. If you this top guy is dA vector dt dot b vector. This one right here is a vector dot db vector dt. Remember, we already just said it. We said that a vector was equal to ax I hat, ay j hat, az k hat, and db vector dt is dbx dt I hat, dby dt j hat, db z dt k hat. I guess it's easier to visualize than it is to write down sometimes. It just takes a long time to write some of this stuff. But if you look at it, well, there's a vector for you. Here's db dt vector for you. If you go a vector dot db dt vector, it's just going to be ax I hat dotted with dbx dt I hat. I hat dot I hat, it's gone. The I hat dot I hat is 1, the scalar 1. Ayj
dotted with dby dt j dot j is 1, just like I dot I was 1, and it's going to be ay dby dt, etc. And then here you go dot k vector dot k vector, it's 1. It's going to be az dot dbz dt. It's the same thing I said up here was going to happen with these guys. Well, at the end of the day, I mean, that's pretty significant. I mean, at the end of the day, we look at it, and again, how they look is how they look, you guys. We went from here up to here, and, you know, at some point we got to write this, so let me see how we're going to write it. Just arguing here with myself where to go with this, I guess, where we want to go. All right, we got enough of these. We saw this. And this is going to be useful. It's the same argument, some of the same argument that we're going to use when we talk about the cross product. But right now, okay, so let's see what we got. What happened? Well, I mean, again, we just said what happened, basically. It was rather long-winded, but what just happened? All the top business right here, dax dt bx, day dt by, daz dt bz, is basically this. dA vector dt dot b vector. The other one, ax dbx dt plus ay dby dt plus az dbz dt, comes out to, well, it's all a's, no derivatives associated with the a's, all derivatives are associated with the b, and if you do the dot product, we know the shorthand, we know the conclusion. We got that for the bottom. The other one here, the A's got the derivatives associated with them, and the B's don't. And you're down to here, and that's the end of the answer. It's the end of the answer. Yeah, we've seen that. We proposed that. We've seen that before, one place or another. And here's a proof of it. Now, again, all of these proofs make sense if either we go back somewhere in work that perhaps I tried to show, or certainly what other people have shown way before I ever did something like that. Wherever you go, remember, what is the mathematics involving the dot product? How do we prove the dot product and have it apply in all circumstances in three-dimensional space? We've talked about that. Utilizing some brilliant mathematics that great mathematicians have done long before I ever attempted something like that, and long before other people have attempted something like that. We used a lot of what they had to say. The great mathematics that mathematicians prior to us have employed. We use that, we know how to do it. How does that dot product work? How does the cross product work? We know how to do that. We consulted brilliant people. I tried to consult brilliant people to show me how to do it, and they did great. You know, so there's a lot out there, you guys, that we can do, that we can look in the documentation, and it's there. And a lot of times, one of the best things any teacher can do is look at what those great mathematicians have done and try to put it together a little bit. Try to repeat it in a manner that's
that's fair enough for the students to look at and kind of get a gut feeling for what's going on. So we know that's true. Okay, we know that's true. How is this thing going to work with the cross product? Okay, we know this is true, guys. And we've set some stuff. Let's see what else we can say here. So we did all this. And we know how to do that. We know how to do it. Again, what the mathematicians knew, different mathematicians did different things at different times, and some things they have documented differently than other people have done. Some mathematicians haven't really took numerous things that we look at, and to them it was already kind of like they treated it as it was understood, and that maybe they didn't emphasize it. They perhaps chose not to emphasize it anywhere near as much. Nowhere near as much as what they really could emphasize it. Other mathematicians maybe ignored other things, but they emphasized other things. So you're going to find different emphasis in different places. There's simply not the time for all the mathematicians to explain everything that is out there. So they pick and choose what they do, and they do some brilliant work. And we've used their brilliant work, you guys, to look at some of the stuff that's going on. This is among the things that they were able to conclude. And we're able to look at that and conclude that for ourselves based on the mathematics that we've learned. Okay? So you know that's the case. You're doing okay. It's not bad at all. If that's so, this thing's really looking right at us. So it's here. Let me erase quite a bit and leave some in there. It's debatable what I want to leave up here now, guys, to be honest with you. I'm almost thinking of taking that and putting it way over there, but as long as it's here, it's here. So let's see what we can do. All right, guys, it's a preliminary course, I guess. We'll kind of leave what I've not erased there. We'll kind of leave it for now and see some stuff that we might want to say. All right, well, I think it's going to help us out. I think it's good for us to know it. It's here. Let me not write it down again, since it's already right here for us. And it's remarkable, guys. Even those great mathematicians, great scientists, Nikola Tesla, Albert Einstein, all of them, Archimedes, Gauss, Newton, they all had to stand on shoulders of people that also knew what they had done, and so on and so forth. Nobody can do this in and of themselves. They've got to look at great resources that have been there, and even the people who had provided those great resources, they had to get them from somewhere. So nobody's able to kind of just do this all by themselves, guys. You need help on this, and we all need help on this. Certainly myself, and that's what we're getting. We're using these great conclusions that great mathematicians have given to us, and you and I are learning. We're having a great time doing it. So we look at something like this, you guys. How are you going to Well, here we go again. Now, the last time I pulled the, let me just say this and kind of put it to rest, I guess you could say. A vector cross B vector. We know what that is. And what's going to happen is, I'm just debating this left and right. I left it like this, and I was saying I was getting the derivative. If you're getting the derivative, then get the derivative. I had, in one place, I had actually done this, actually written derivative like this, and in the other place when I was doing it, I just left it as A vector cross B vector. So I was careless on that. That's one more reason I'm doing this. In addition to the chalk being better quality, I think you can see this a lot better as well. So there's a number of reasons I'm doing this. So you're looking at this. Well, yeah, that's something. I mean, they're making. Let me almost put
the horse in front of the carriage, as they say, there is a claim, and it is a true claim, and we're going to prove it, that you're going to get dA vector dt cross B vector plus A vector cross dB vector dt. It's absolutely true. And in fact, that, you know what that means? Just kind of keep in the back of my mind, I'm kind of debating. I didn't really do this last time, or maybe I did. I don't think I did, though. One of the films I had here. Ladies and gentlemen, that is the same as, what is that? Well, what's any cross product? Man, we went into some very big detail regarding the dot product and the cross product and how to prove, we proved what in earlier films, I don't know what's early relative to you, what you might be looking at this first, but there are other films out there, and they're earlier than this particular film that we're doing right now. In that sense, in earlier films, we have discussed a proof of what the dot product is. We've discussed a proof of what the cross product is. We know how to do that stuff. I vector, I hat, j hat, k hat, dA vector dt is dAx dt, day dt, daz dt. The order matters. Okay, that one's here. It's in the middle. It's right here. It's the first. It's above what B vector is. What's B vector? B vector is bx, by, bz. This is I hat, j hat, k hat. It's ax, ay, az, dbx dt, dby dt, dbz dt. I hope I'm writing about as big as I can write, guys. Yeah, look, let's get something straight. I'm not, if this is equal to all that, then all that is equal to this, obviously. If this is equal to all that, then all that is also equal to all this. All this is equal to all this over here. Okay, that's the claim. What does that mean? That means that everybody stays within this format. Everybody stays within this format twice. There's going to be, well, here's what it means. Notice how all the orders are right. A is right below the IJK, B is right below the A's. The A's are right below the IJK, the B is right below that. Here the A's are also, just like over there, below the IJKs, and the B's, just like over there, are below the A's. But there's just derivatives in different places. What does that mean? That means this format, ladies and gentlemen, is going to occur twice. This format is going to occur, you know, and I'm sort of putting the carriage in front of the horse on this thing, how they do it, but what the heck, we got this far, we might as well do it. Everybody's going to have this look. What does that mean? That means whenever you're dealing with the first determinant, you got dA dt, dAx dt, day dt, daz dt. You got dA vector dt. All the A's are going to have a d dt associated with them, and they stay right there. Then you go over here, and all the B's are going to have, now contrary to that, all the A's are derivatives, and that's simple as that, but the B's stay as is, and they stay with this exact same format, my friends. Here, same argument, exact same format, but it's going to be the dB's, dB dt, dBz dt, dy dt, dBz dt, dBx dt, dy dt, dBx dt. Whereas earlier it was dy dt, daz dt, dax dt, daz dt, dx dt, dy dt, etc., etc. It's that same format though. So they're claiming if all of this is true, they're making the claim, let's do it. They're making this claim. I'm sort of putting the carriage in front of the horse, but I'm not worried about it. I'm going to write this out, and then I'm just going to confirm that this indeed is true, but I'm going to prove it. So it's not like we're doing something haphazard here, saying, oh yeah, we're doing this, but you're already kind of giving too much of a hint. No, I'm saying this is what we are trying to get. This is what we're trying to get. Let's see what we can do. Okay, here's the look. The first scenario is with the dA vector dt. So all the a's are going to have that associated with them. So let's see what we got here. We're going to have day, if it works, if it's true. I mean, here's bz minus daz dt by plus a negative j. See what kind of room I got, guys. I'm always a little apprehensive. You guys can see what I'm doing actually. BZ. This stuff is easier to at least see as a format. DAZ dt. And again, all of these are functions of t, guys, so it's not an issue there. Not an issue there. There it is. Plus k hat. dax dt by day dt bx. Okay. True. That's this. Plus, and here we go again. Now we did the first one. The first determinant looked like what I just wrote over there, upper right-hand corner. The second determinant, it's going to look identical. How's it going to look identical? Well, here's an AY, and this one's going to be dBz dt. Oh, here's an AZ. There's going to be a dBy dt. Plus negative j dax dt I did not want to write that. I wanted to remember now I'm doing the second guy, which has got the b's right here. But everybody's in the same order. It's hat vectors, it's A vectors, it's B vectors. Hat vectors, A vectors, B vectors, if you allow me to say it like that. It's all the hats, then the A's, then the B's. All the hats, then the A's, then the B's. It doesn't change. So when you're going to evaluate, you just respect what's in there. But ladies and gentlemen, I can't emphasize this enough. It's the same format as I have right here. So what do we have? AZ dBx dt. True. And
of course, I ran out of room. Write that. Let me see if I can find a little bit of room here. Okay, I'm sorry. Here we go. All right, you got that. Here we go. AX dBy dt. AX dBy dt. Minus AY all right, guys, it's none of this is, I mean, it's just, you always wish you had a little more room, I guess, right? But look, there's a moral to the story here, and it's it. I mean, you're saying this thing breaks up into two things that look like this. It breaks up into two things looking like that, having that format, having this format. Looking like this, having this format. Looking like this, having that format, and these two guys each have this format. Okay, that's the claim being made. Tell you what, at least I know what to look for. Doesn't mean I'm going to get it. Doesn't mean that I'm going to get it. Could be wrong. I mean, it's not wrong. I don't want to say it could be right. It's not wrong. The stuff is right. It's correct. But let's say hypothetically, in our mind, we're thinking, hey, we could, anytime we're trying to do a proof, we could prove something that kind of disproves what we thought was the truth. Well, we already know what the truth is on this. It's been proven time and time again by great mathematicians who preceded us. Okay, so they have it right, and we're going to confirm that they have it right. So we're looking at this, and is it going to play like that? Is it going to look like this? Yeah, I think so. The way you're going to do it is, you're going to take, we're going to confirm that. You're going to go d dt of what we know A cross B is. Yeah, we're going to confirm that is what it is. That's for sure. Now let's find out what that is. Well, if you're going to do that, you're basically, you are getting the time derivative of A vector. You're getting the time derivative of A vector cross B vector, which is the time derivative of this determinant, which is the time derivative of all of this. Well, how do you do the time derivative of all of this? Well, the vectors don't leave. The I hat, j hat, and k hat stay. You're going to have to do the product rule. You're going to have to do the product rule right here. Then you're going to have to do the product rule right there, then right there, then right there, then right there, then right there, and see where it goes. Well, what you're going to do is, when you actually do this, what we got here, product rule right here. Now let me, we can argue this a bunch of ways. Let me try to make this somewhat easier.
theoretically I want to write this smaller, but I mean, there's no point if people can't see what I'm writing either. I want you to look at this right here. I want to take a close look at that. Do the product rule right here. For AYBZ, do it for AZBY, do it for AXBZ, do it for AZBX, do it for AXBY, do it for AYBX. You get the picture. You're going to do this 6 times. 2 for the I-hat. 2, you're going to do it in 2 different places for the I-hat, 2 different places for the J-hat, 2 different places for the K-hat. AYBZ. Let's do the product rule right here. And then we'll kind of just move from there, and I think we don't deliver too much of a speech. AYBZ is going to be and I'm going to try to, I think we all kind of feel where it's going here, guys. We just got to hopefully build some room to do it. If I got to move this thing around, I got to move it around. But this J is going to be tough. There's not a whole lot of room there, guys. But let's see how this plays out based on study. Now, we've done this before. We've talked about this. Let's use product rule everywhere here. DAY dt BZ plus AY dBZ dt. That's just this guy right here. Don't let the minuses scare you. Don't let the subtractions scare you. It's going to be here you go, that's plus. It's going to be minus DAZ dt by, etc. Plus, just this guy. Don't worry about the minus. The minus is already taken care of. I put the minus there. Now do the product rule for this guy. The minus is already accounted for. AZBY. That's DAZ dt by. That's AZ dBy dt. Yes. The minus is already accounted for, guys. Definitely am going to run out of room with this one, guys. Try to give myself a little more room. AXBZ. You know where I'm going, guys. I mean, by now you know where I'm going. AXBZ AXBZ. And you do the funny business here with this. True. Buy myself some room, you guys. AXBZ. Do the business with the AXBZ. I did it. Do the business with the AZBX. Doing the product rule. Sure. Do the product rule, AX BY. Do the product rule on AX BY. Yeah. Do the product rule on AY BX. Look, I'm the first person to tell you that this is certainly a mess. What's going on here? Well, there are minuses everywhere. Yeah, I know. Don't worry, the minuses are going to hit everybody consistently. If the minuses are going to hit everybody, I don't know, it's what you want to say here. I'm going to debate this a little bit with myself, guys. Minus that. This minus that. Also take and, yeah, do it right here too, for the top guy. Also take this guy. Get this guy. Do that with the bottom one, guys. How about the blues with the blues, the reds with the reds? I don't know how visible this is, guys. I'm going to err on the side of caution. I'm going to go good old dependable green here. Green on top. And the other one is the red on the bottom. What do we got? We got top here, top there. Top minus top. We've got top minus top. We've got top minus top. Wait a minute. All the tops are dy dt, daz dt, dax dt, daz dt, dax dt, dy dt. And the other b's are just the b's that were there before. They're exactly here. Let's see what we got here. dy dt bz, daz dt by. dy dt bz minus, let's see what we got here. Look at it carefully. dy dt bz minus daz, dy dt bz minus daz dt by. dy dt bz minus daz dt by. True. I'm over here. dax dt bz minus daz dt bx. dax dt bz minus daz dt bx. I know it's plus a negative j. I already have that accounted for. I know there's a subtraction here. You know, I know there's a plus a negative j. I got that accounted for. Don't worry about it. So leave it be. Find out what's going on here. Within here, there's a subtraction. Yeah, there's one right here too. dax dt by minus dax dt by minus day dt bx. Dax dt by minus day dt bx. You got it. True. Okay, I just took care of the tops. How about the bottoms? Ay dAbzt. We're making the claim that's the way it works. Set them up. So work with the bottoms now. We figured out the tops and got all this right here. Now work with the bottoms. Get all this. I-hats. Ay dBz dt plus Az dB. I think that should have been a Y, guys. It should have been a Y right here. I'm sorry. Ay dBz dt plus Az dBy dt. Ay dBz dt minus Az dBy dt. Got it. That's the bottom here. Bottom here. Ax dBz dt plus Az dBx dt. Ax dBz dt. Time out. Let's see. Make sure I got that one. Okay, let's see. Right. I'm sorry. I was looking at the wrong one for a second, guys. Ax dBz dt minus Az dBx dt. Ax dBz dt minus Az dBx dt. Fine. The negative j hat is already there. The minus is there. I've accounted for that. The minus is accounted for right here. The minus is hitting everybody in here. These guys are all addition. Addition, 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 addition. Everybody's addition. But the minus distributes itself. And the minus that's right here eventually will distribute itself as well. Right now, I'll leave it there. But I've got everybody accounted for. Ax, let me see here exactly what I wrote. Right. So I got Ax dBy. This is not legible, guys, to save its life, but here it is. Ax dBy dt minus Ay dBx dt. Ax dBy dt. Yeah, right, the very low one. Ax dBy dt. Ax dBy dt minus Ay dBx dt. But he's there. Everybody here is correct. And if I associate all that has to be associated the way that it should be associated, then we're okay. All of this is correct. Now let's just associate them and make them look like this. Yeah, but where did that come from? Well, this top part is indicative. Regardless of whether I wrote this down first, you guys, if I set them up in such a way that all derivatives of A are up top and all derivatives of B are on the bottom, or wherever you want to put them. I mean, here's a row of all derivatives. Here's a row of all terms involving derivatives of A, but no other kind of derivatives, just derivatives of A. And here's another row involving all derivatives of B and no derivatives of A, no other kind of derivative. So that's what I have. So I have all derivatives of A associated with this, all derivatives of B associated with this. Where is that? What is that? Well, even before I was saying everything I was saying, that right there dAx dt, day dt, dAz dt, and here's bx, by, bz, that's the first one. That's all this. This, I mean, I don't know how many circles I don't know how many times I'm gonna highlight this to the point we're not gonna even be able to see it anymore, I guess, but all this right here is the first one.
That right there, this top one, is that determinant. This bottom one, and I mean it is a, look, I'm not gonna even pretend to say, it's kind of a mess, but you know where to find it, you know how to look at it. You can get it on your own as well, guys. You're not gonna have an issue with that. This second one arises from this, and now I absolutely have no room. Unless I write smaller, and I'm always apprehensive, I want you guys to see it. AX, AY, AZ, dBx, dt, dBy, dt, dBz. And that's equal to all of this. All of this, all of this right here, all of this right here is equal to this. Yeah. Absolutely. It's the moral to the story. Yeah, the moral to the story is, at the end of the day, I always forget we do have the back button. Yeah, it's equal to this, is equal to that. I don't really want to erase any of it. But at the end of the day, you saw it. It's all true. The first vector, the one on top that I got circled, this circled, plus the top circled, plus the third top circled, is this guy. The bottom part circled, plus this bottom part circled, plus that bottom part circled, is this guy. Absolutely true. All right, I mean, and there it is. And again, the last time I had done something like this, guys, I had failed to put DDT. I'd failed to put DDT next to the A vector cross B vector. And somewhere else, I still had it there. It was still on the board, and probably people could see, hey, wow, he's making a mistake here. He should go DDT on that because he has it somewhere else. That's the likely scenario. People are going to catch that mistake I made. Worst case scenario is maybe they didn't catch that mistake and they're starting to believe the mistake I actually made. So I wanted to do this again. There was other stuff I had said there that's very valid and can help us out, so I'm kind of opting to leave it there. Just be aware of it. But this is where it's at. Wow. They're saying some stuff. You know, it almost looks like, okay, from the standpoint of trying to be intuitive, so to speak. You know, it seems, oh, gee, it should be like that. Now, there's a lot of things that look intuitive, doesn't mean they're actually true. And if they are, and a lot of times they look like intuitively they should be true, but there's a lot more mathematics behind why they're true than us just looking at it and saying, oh, the aesthetics look right, therefore it must be right. There's much, much more that, so often there's so much more than that which meets the eye. There's so much more that meets the eye, guys, regarding something like that. Let me leave that here. Let me write something else over there, just right next to it, and we'll kind of just talk a little bit. And we said this too. All right, guys, and we've been there. And like I said, if you want to take subsequent derivatives, it's the same exact argument. It's the same exact argument. You just have to be cautious because there's going to be more terms involved, but they're going to be within the format of the discussion that led us to here. They're very much within the format of the discussion that brought us here. It's not a lot of complicated mathematics at that point. Once you get to this, and you're confident you've done it, and you've looked back at, hey, if you really want to get rigorous about it, how do we prove what the dot product is in three-dimensional space? How do we prove what the cross product is in three-dimensional space? We've been there. Once you go there and they say, okay, now let's take a derivative. If I want to take a higher order derivative other than this, go ahead. You know the rules. Watch it. I mean, but the format is there. There's just more items there, and just watch out. Watch out. But otherwise, it should be pretty straightforward. Okay. Should be okay for us. Want to go higher than that. Dr. Katz in her brilliant book talks about, say, in Physics for Scientists and Engineers, Foundations and Connections, Volume 1, on page 379, they talk about a couple things here. They talk about angular momentum in terms of what you're going to say in terms of momentum, you guys. Now, I've talked to people in different contexts over the years regarding how you want to view something, and sometimes we throw vectors kind of out the window a little bit just to get a gut feeling for what's happening in certain special case scenarios, and then we kind of say, okay, by the way, in a more complicated format, the same dynamic is holding, you know. So I'll tell you what. I mean, there's a lot that can be said, guys, but we've said, I think I said this the last time as well, let me just kind of be careful how I do it.
there is the idea in the linear realm of mass, and that looks a lot like moment of inertia. And the moment of inertia of a point mass, of one point mass, a distance r from an axis, is mr squared. And if you sum, and we're going to get, you know, at some point or another, I think we're going to get into this a little bit when we talk about it. I is equal to the summation mr squared, appropriately done. There's a lot you can do here. I mean, in the calculus realm, that becomes a different dynamic. You know, you're doing something of the nature of, let's see how you'd want to say it. I mean, you got r squared dm, where for a small mass and you're getting distances, you can get something like this. So all of this holds. I'll talk about it. We'll see exactly when I'm going to talk about it. Hopefully soon. I mean, like even within the context of this video, we might come to this. But anyway, I mean, for our purposes, they talk about this, and we'll come to this, and I'll discuss it in a certain way whenever that's going to be discussed, guys, either in person or on film. I'm going to try on film in very short order to do it. But so we're looking at something like this. Look what I got up there. So moment of inertia, I, and mass are analogous to each other. This is translational realm. This is rotational realm. V, it's a vector, and omega are analogous to each other. Both vectors right now, let me not write down vector. Let me just say V. The speed at which something is going, or the speed of its rotation as well. V is velocity or magnitude of velocity. Omega is going to be the magnitude of the rate of angular rotation, revolution. So look at something like this. A is acceleration, alpha is angular acceleration. So this is mass, this is moment of inertia. Linear realm right here, angular realm right here. Linear realm right here, angular realm right here. Mass is analogous to moment of inertia. Velocity is analogous to angular velocity. Acceleration is analogous to angular acceleration. Force is analogous to torque. What torque does in the rotational realm, it'll tend to cause a change in rotational status. Force will tend to cause a change in a linear sense. Now, the force and torque are closely related. You got to put force on something to actually establish a torque. So it's so on and so forth, you guys. They say stuff like this. If they say kinetic energy is 1/2 mv squared, in the rotational, 1/2 I omega squared. I looks like mass, omega looks like v, 1/2 mv squared, 1/2 I omega squared. I looks like mass, omega looks like v. So on and so forth. We said, come over here. We said that work is force times distance. I'm not going to get too obsessed with the R dot products, guys. There's a lot more that comes to this, and we're dealing with things in a vector sense. But right now, let's just get some kind of gut feeling without really touching the vectors for a bit. How good an idea is that? We can debate that one too, okay? But we've gone into vectors exhaustively. We just went into it, and that's what we just did. And we've done it before. So we know how to do the vectors when we have to do them, okay? But right now, let me just say work is force times distance. Let's say they run parallel to each other. Work is equal to torque times theta. Because distance, see, I didn't write that down earlier. I'm going to write it down now. Distance and theta are analogous to each other, where theta is in radians. And that's the lingua franca on that one, guys. That's what
need to use on that one, so on and so forth.
Isn't work divided by T equal to power, the rate at which work is being done? That's FD divided by T. Wait a minute. Isn't D divided by T equal to V? That's FV. Yeah, I wonder how that works over here. Well, it'd be good to know how this even worked to begin with. Torque is force times distance. It's force times perpendicular distance to it is what it is. It's from where, you know, for there to be a torque, if the radius, if R, the moment arm, the direction in which you're pushing and the actual moment arm itself are parallel to each other or anti-parallel, you're not getting anything. It's the best way to use a lever is not push into the lever, it's to push perpendicular to, you set the lever somewhere and you push in a direction that is perpendicular to the lever arm. If it's perpendicular to the lever arm, it's FR sine theta. It's R, you know, in the strictest sense, torque is R vector cross F vector, which the magnitude of the torque, let's just call it tau, is FR sine theta, the angle between them. If the sine is 90 degrees, then it's just FR. Torque is F times R. Well, yeah, there's a lot that gets said here, guys. There's a lot that gets said here. Let me try to say it, I guess, because there's other stuff we can say when we need to say it. Okay, so we got this right here, guys. Eventually, I think I'm gonna need a little bit of room. Well, let's see here, guys. There's stuff going on here. We kind of come back here a little bit, I guess. We know distance traveled is, in the rotational realm, is the length of the moment arm times theta. Theta is in radians. R times theta will give you the length of the arc that you have traveled. If you look at it, that's D, this is R, this is theta. Theta is the ratio of the arc length divided by the ratio of the arc length to the radius, D divided by R. If you multiply by R on each side, D equals theta times R or R times theta. We can debate that one too, however we want to write that. They mean the same thing, right? Theta times R, R times theta. And that's in the rotational realm. If you took, you know, D, and I guess you could give it a couple, you call it X if you want, doesn't matter the length of this. Let's go with X, but I called it D elsewhere. That doesn't really matter, guys. Same kind of argument. You understand that V, or the magnitude of velocity, don't want to get too touchy with this whole thing. I mean, they are vector quantities, and we can go there when we need to go there. But right now, let's get a gut feeling for what's happening here. V is dx dt. Is d r theta dt. R could change. Hey, we're talking about the product rule again, guys. We could go dr dt theta plus r d theta dt. That's another dynamic in its own right. But right now, let's leave r to kind of not change, but only theta is changing. If that's the case, if r doesn't change, then you got d theta dt. Well, d theta dt is omega. R omega or omega r. Interesting. You know, we can come back to some of this stuff too, guys. I'm going to come over there. You already have this up here. I'll come back to it again. Just, running out of a little bit of room again. At least remember what torque is here. So when I get back to it again, let's see if we can say some stuff. Got another question for you. Isn't A dv dt, which is d squared x dt squared? Yeah. Well, yeah, okay, great. What's dv dt? Well, we just said v. We kind of cut ourselves a break here. We didn't make r a function that was varying. We made it a constant function. Doesn't have to be, though, constant. If it's not a constant function, then when you're doing this, d of r theta becomes, if you were going to do it, if r was in the strictest sense, that's the product rule. So it'd be r, let me see here. dr dt theta, r d theta dt. Yeah, we said this thing ain't changing, so it came out to 0. That's not necessarily true, however. It does, if it's a constant function, yeah. But if it's not, you can't say that. Well, we said it. We said, okay, just use it as that. This is, well, it's dv dt, right? So it's, again, dv dt, which is omega r. We're saying r stays constant. The omega dt, the rate of change of angular velocity is called the angular acceleration, r alpha, or alpha r. So wait a minute. Something going on here. Here's linear, here's linear, here's linear. It's linear behavior, however, the stuff's still going around in a circle. If you allow me to say that. I'm just finding the linear speed as this thing goes around the racetrack that's a circular racetrack. It's still going around a circle, but I'm getting the linear speed, the tangential speed, so to speak. The tangential speed as this thing whips around a circle. So that tangential speed is like linear. Now, we're not talking about an omega in a sense. We're just talking about, okay, how fast is it going at that point, at the tangent, if it was like to fly off. Tangential, tangential, tangential. Or, let me say linear, linear, linear. Yeah, I know. But the linear came from something associated with rotation. The linear came from something associated with rotation. The omega. Rotation got us that. Rotation got us that. And rotation got us that. So there's definitely a connection here, and multiply by r. I is a little different. You know, m and I are associated with each other, but each differential element is of the form mr squared to get the I, to get di. The di would be dm r squared, etc. Okay. So there's a lot going on here, guys. There's the linear and there's the rotational. If you allow me to say linear. In other words, even though everybody's going around a circle, you're finding how fast it's going around that circle. True. Okay, if it were going in a straight line, I guess it would behave like this. V would be as big as omega times r. A would be as big as alpha times r. D, the distance covered, is the angle theta times r, is what they're trying to say regarding that. So, if you're going to look at something like that, guys, it's present there. I went into this the last time. I did something like this. It went, I think, relatively decent on that. But yeah, then again, this stuff is always good to look at again. Whenever you get a chance to look at something like this, it's never a bad idea to look at it again. Okay, so there's a lot to be said. So little time to say it sometimes too, you know, but so we know that. So linear, so again, the connections are pretty fascinating. You know, we talked about M, we talked about I. We talked about distance or x or something like that, x or y, x, y, x, whatever. You know, so it could be distance, it could be x, it could be y, it could be r, it could be a lot of stuff. The analogy there in the rotational realm is this. V, we got omega, A, we got alpha. We talked about force. We talked about torque. Pretty interesting stuff in its own right regarding that stuff, you guys, and so on and so forth when we do that. So we talked about x being theta times r. We talked about V being omega times r. We talked about A being alpha times r. And so we got this. If the torque, you guys, is, and again, it's in the back of our minds here, we've got, you know, the work that's done is force times distance. Tell you what I'm going to do. Isn't the distance traveled theta times r? Didn't we say r times theta? R times theta is the distance. R times theta is the distance, or theta times r is the distance. If this is distance and this is force, then that's work. Might need some more chalk, guys. Yeah, I mean, this theta times r is distance, F is F, F times distance is work. Okay, I agree. What do you say you use the associative property? Put the F and the R together, put the theta right here. Wait a minute, F times R is torque. And that's where they're getting this. And that's where they're getting this. And that's why when you're doing, they say, okay, well, work is equal to force times distance. Wow. I mean, the analogy's alive and well, you guys. Work equals force times distance. Didn't we say force kind of sort of looks like torque? And then we say that distance kind of sort of looks like theta. Theta and distance, angular displacement and distance are analogous to each other. Torque and force are analogous to each other. Wow. Work equals force times distance. Work equals torque times theta. Crazy. What do you say you divide by t on each side? D divided by t is magnitude of velocity. Rate at which work is being done is power. Distance divided by time yeah, it's working. Wonder if it works here. Take work divided by time. The rate at which an angle is increasing or decreasing. Let's say it's just displacement, so we're just going to say it's increasing in some sense. It's going somewhere. The rate at which an angle is changing in relation to time, theta divided by t is omega. Work divided by time is power. Torque is torque. Theta divided by t is omega. Man, here we go again. I hate to say it. Yeah, force looks like torque. Magnitude of velocity looks like magnitude of angular velocity, magnitude of angular velocity. Simple as that. Okay. A lot going on, guys. There's a lot of analogies. I mean, we can see it. I mean, it's staring right at us. I mean, how do you calculate work? Well, how do you calculate work in one realm or the other? How do you calculate power in one realm or the other? And that's a lot of it. And look at this right here. Look at how they sure look. I mean, they're off by an R. You know, the moment of inertia is R squared. It's a little different dynamic here, guys. And right here, this is not R times bigger than tau. Tau is, in a sense, R times bigger than F, in a sense. It's F times R. Okay, right. But those three kind of stand out at us. Again, the book should go in that as well with you guys. Should go into that as well when they talk about some of this stuff, you guys. The interesting thing is they've got, you know, and this is kind of where the derivatives and all other stuff come into play. We talked about force itself, you guys. Force equals mass times acceleration. That's m dv dt. But remember, mv, the rate at which mv is changing, if you divide it by time, v divided by t is acceleration, and that's where we're getting the momentum. If it's in terms of, in the strictest sense, these are vectors we're talking about, make it a vector quantity. The v vector divided by time is m dv vector dt. Now, for all we know, m could be changing too, you guys. I got this for an answer. Technically, this right here should be, I'm sorry, that's not momentum. It was momentum, and then we took the derivative of it. This right here is force, forgive me. That's force, forgive me, that's definitely force. If we were to take momentum, which is mv, that's momentum, and divide it by time, allow me to do it in a very rudimentary way here. Momentum is mv divided by time. That's ma. That's equal to force. Yeah, I know, but I just said that was momentum early on. Momentum divided by time. Yeah, I got a little more subtle. Yeah, that's true. That's true. I got a more subtle way to write this. Or maybe a more precise way to write it. P divided by t, how about dp dt equals force? The change in momentum. There's a lot that can happen here, guys. What's going on here? Well, you saw it. You saw what was going on. You know, if I were to find the change in momentum divided by the change in time, that's delta p vector. Let's say these are vectors. Again, I sometimes, for the sake of some kind of simplicity, you can debate how useful that is and everything else. The change in momentum divided by the change in time. In the limit, that goes to this. Okay, let's lose the vectors for a second, just for a second. So we kind of just tinker with just do some flat out math with this stuff without going into vector analysis on it. dp dt would be the change in momentum with respect to time. I was sort of putting forth that argument in a number of places here, especially here. You know, here's the momentum, here's time. A better way to do it would be to say, you know, how are we going to, you know, how does this stuff change? I mean, the way it works is, like we said, force equals mass times acceleration. That's mass delta v over delta t. You know, in the limit, that's going to come out to mass dv dt. Okay, I guess we can accept that. Yeah, but I tell you what, why don't you go m delta v over delta t like this, and this up top is really a delta p, delta in momentum over delta t, and in the limit, that's going to go to dp dt. Now, what's the big deal? So what? What are you talking about? What if the mass is changing? What if there's an acceleration taking place, but this thing is gaining mass as it's also speeding up? Somehow things are being thrown onto this thing. Things were being thrown onto this wagon as it was picking up speed. It's not only going faster, it's not only accelerating, it's not only having positive acceleration take place, but you're also increasing the mass of this thing while it's happening. Wow, it's even more force. There's got to be more force on this thing for that to happen because it's gaining mass and it's gaining speed. What if it's losing mass but gaining speed? Well, then we got to look at it. We got to tinker with it a little bit. That's kind of where this comes in. dp dt, if p is equal to the function mv, here we go again. We've been doing the product rule all day long, it seems. Do the product rule here. The derivative of the product is the following according to the product rule. Usually people are allowed to stop right there because there's no change in mass. But in a rocket, there is change in mass. So it becomes very important. So they both become significant. Oftentimes, dm dt is 0. If dm dt is 0, you got this. Well, there's a lot going on here when you do some of this stuff. I mean, with some of the mathematics that's there, let's at least talk about that a little bit. Okay, so we say, yeah, that certainly can happen. What's happening here? Well, we said a couple things. We saw what happened. In the strictest sense, F vector is dp vector dt is dm v vector dt v vector, m vector, I'm sorry, not m vector, essentially what we've been saying, guys. We did the product rule and we got that. True. And torque is our vector cross F vector. True as well. And how does that play out? Well, it plays out the way everything else plays out, I guess you could say. If you're looking at this, there's a lot of ways we can talk about it, I guess. How do you want to do this? You know, I mean, where you want to put this thing? Where F can have a mass. F might have a mass associated with it, or it might not. Let me come back and associate a mass with it at some point, but not now. Let's leave that as that. We can say this, that you got this, and you want to say, just want to talk a little bit about this. You're going to see how this can be confirmed in a sense. You saw what I did here to get, we went from here to here to all this. So they're making an argument. Let me kind of just say this again. I'll just say it again, I guess. F vector is the time derivative of momentum. I don't want to get into all the specifics of it, But let's say that's true, and we've seen enough of the specifics that I think it's believable. Okay, yeah, true, it is. There is something of interest here, guys. You can say that L vector equals R vector cross P vector. Now, L is angular momentum. Momentum in terms of size is mv. For our purposes right now. Momentum is mv. Angular momentum is mvr. mvr. Sine theta, a whole bunch of other stuff you can say regarding that. So, mvr. This is P, this is R. That's P, that's R. Here's P, here's R. P times R or R times P. R cross P is how they define it. Let's talk about it. We said that force was the time derivative of linear momentum. I wonder, the time derivative of linear momentum gave us force. What's the time derivative of angular momentum? Well, it's a good thing we just did it. Yeah, we just said L vector, angular momentum vector, is R vector cross P vector. Yeah, good thing we already did this one. We've proven this in some pretty excruciating detail, haven't we? Remember A vector cross B vector? The time derivative, the first derivative with respect to time of A vector, the first derivative with respect to time of A vector cross B vector is, you know what it is. I mean, we've done it, you've seen it, and we're going to do it again. This is A vector, this is B vector, if you wish. And we got dr vector dt. Dr vector dt is V vector, the velocity, the tangential velocity at a particular point. It's dr dt, let's see here, exactly. Yeah, right. Dr dt cross P vector. What was I thinking? There it is. Okay. And the other one is R vector cross dp vector dt. Fascinating. Ladies and gentlemen, dr vector dt dr vector dt is V vector cross P vector is M V vector plus R vector cross dp vector dt is F vector. That right there is the torque. What is the... Be careful here. This right here is the torque. This right here is of great interest. V vector cross product with M V vector. If V vector is doing this, and let me just draw a little bit above it, but they are collinear, guys. If this is M V vector, and this is V vector, and they are collinear, my friends, that's MV, that's V. So this is, the long one here is MV. And the shorter one here is just V. If they're collinear, what's the cross product of two items that are collinear? If two vectors are collinear, remember the cross product is according to the right-hand rule. It's the magnitude of one times the magnitude of the other times the sine of the angle between them, and then the resultant vector is perpendicular to that product. The resultant vector is perpendicular with a is perpendicular to those two vectors. The resultant vector is perpendicular to those two vectors in a right-handed fashion, having the magnitude of one vector times the magnitude of the other vector times the sine of the angle between them. And it's perpendicular to those two vectors. The resultant vector is perpendicular to those two vectors in a right-handed manner. True. All of that is true. Problem is, it may be perpendicular to those two vectors in a right-handed manner. The resultant vector, the resultant vector, the cross product is perpendicular to those two vectors in a right-handed manner and has a magnitude equal to the magnitude of one times the magnitude of the other times the sine of the angle between them. The sine of the angle between these two is 0. Forgive the long-winded discussion, guys. The sine of 0 is 0. This guy right here is 0. They're 0. These guys were this and this are the same. It's 0. The only guy left over is this guy. And that's the torque. And that's the torque. Torque was equal to this. What is going on here? Well, you just saw what's going on. I mean, basically, at the end of all this, the magnitude of that is equal to the magnitude of this, and also behaves according to the dot product as well. I mean, so the long story short is the following. F vector is dp vector dt, and the torque vector is dl vector dt. Why is that so? Because it's d r vector cross p vector dt, which is equal to dr vector dt cross p vector plus r vector plus r vector cross dp vector dt. dp vector dt is f. This is r vector cross f vector. That's what this is. This right here is dr dt is v vector. dr vector dt is v vector. This is m v vector. These are collinear. The cross product of two collinear vectors is 0. R cross F, that's torque. Yeah, that's torque. This guy right here got us the torque. The derivative, dl vector dt is d of the cross product r vector cross p vector dt, and it gave us all this. Yeah, the end result is that. I'm sorry, r vector cross f vector. R vector cross f vector. R vector cross f vector is what that's going to be equal to. It's what's that equal, is what's equal to that. This guy right here is this, and it results in this because of all that. Well, wait a minute. All that giving you this, that from the get-go was torque. So that's certainly true right here, guys. We got this, just forgive me, guys. This is a lot easier than I'm making it. I'll just try it again here. F vector is dp vector dt, and torque wow. It's another way to look at it. Wait a minute. The time derivative, the first derivative with respect to time of momentum is force. The first derivative, let's try to say it again. The first derivative with respect to time of linear momentum is force. The first derivative with respect to time of angular momentum is torque. Wow. Yeah. L vector and P vector look a lot alike. This is angular momentum. This is linear momentum. This is torque. This is force. The first derivative with respect to time, of linear momentum is force. The first derivative with respect to time of angular momentum is torque. Pretty neat stuff. So we got that. There is and there's more. I mean, there's ways we can say certain things, guys, and everything else. But I get, wow, this is what's crazy about all this is that this sort of mysterious looking stuff that we call dot products and cross products, if we define them, if we see how they behave using strict mathematics to really understand their behavior, to prove numerous things about them, then when we've proven certain things about the dot product and the cross product, using them becomes very useful. Using them becomes immensely important, and it really answers a lot of questions. But for that to work, we have to have the foundation. That's why we wanted to talk about the foundation so much. But now that we have it, it's useful in mechanics, and it's useful in electricity and magnetism. It's useful in a lot of places. So some great mathematics there, you guys, and the people who thought it out really thought it out very, very well. It's very well done, the way this stuff has been thought out some time ago. Exactly when, I don't know, but it's probably a relatively long time ago they had thought a lot of this stuff out. Brilliant stuff that they had thought out. With that in mind, let's, I'm sort of debating with myself. I should do some of this stuff, guys. I think I'm going to let it go at that. I think there's there are good there's some good mathematics, I guess, we can use to talk about the parallel axis theorem. But I've given you that stuff already, and it's on Canvas, and we can look at it. There is, I think I might want to. Yeah, I think the best thing to do is probably leave that for you guys to have it. I don't think William Shakespeare is going to have anything to worry about regarding my rendition of some of the things that I talk about, but it all should be there when we talk about some of this stuff. It should come out pretty good. So I'm probably going to have this scroll, likely have this scroll right at the end of right at the end of this particular video, you guys. So I think this is looking pretty good, you guys. Wish people were here. I could ask you for questions, right? But anyway, that's about it. Thank you very much for your time. Take care.